Hi guys, so what we're going to do in this lecture, or sorry, in this tutorial is quickly just go through an example problem so we can just get started on beam analysis. So we're going to bring in a beam system. We're also going to combine it with a truss element. We're going to have a little bit of a play around with it and see how we can, how both we set up beams and how we can adjust their behaviours. So the first thing is we're just going to create a general sketch. So it's just going to be a little bit of a sort of a crane, like an engine crane sort of thing that we're going to draw up. So we're going to go into parts and create a new part. It's going to be in 3 dimensions, and I'm just going to call it the crane. It's going to be in 3 dimensions, and it's going to be a wire base feature, and approximate size I might make it say 100. Okay. We're going to be in SI units. So I'm going to draw a vertical line down the middle here. So I'm going to draw 1, 2, 3 members, and then from the second, from this point here, which is the second node from the top, I'm going to draw 2 horizontal lines, and then I want to draw 1 line from here to here. So essentially we're going to have these vertical elements and the horizontal elements, they're going to be beams, and then we are going to have this diagonal element here be a truss member, so it can only take normal loads. Alright, now we're going to apply the dimensions to our system. So this dimension here is going to be 2.5 meters. This dimension here is going to be 1.5, and this will be 0.7. The first horizontal dimension will be 1.5, and the second horizontal dimension will be 2.2. Alright, so we should have a system which looks something like that. Now everything's fully defined in here, and we can just exit out of that, and we're done. Alright, so we should have a geometry looking like this. So it's all going to be made out of steel, so I can go in and create a steel material model. So 210 GPa and 0.3 price-lines ratio. I'm also just going to add in the density into this. So we go into general and add in density, and for steel it's about 7,850 kilograms per cubic meter, because again we're working in SI units. So I can just add that in. Now, because we're creating a beam model, well, we became creating, excuse me, both a beam and a truss model, so we need to create 2 different, we're going to need to have 2 different profiles. Okay, so the first profile will be our beam profile. So if you go down to profiles, we're going to right click on that and hit create profile, and we're going to create a I-beam profile. So you can see here when we go and create trusses, we need, if you remember from class, we need not just the area, but we also need to know the second moment of area of our beam element, and we do that by creating our I-beams. So I'm going to just call this my I-beam. Alright, and then you'll be given a profile, an image like this. So we can see here we have all the overall dimensions of our I-beam. We have thicknesses T1, T2 and T3. We have widths B1 and B2. We have the overall height L, and we have this, we have the overall height H, and this height here L, which is the distance from this bottom edge to wherever the center line of our beam is here. So we can see the center line on the left here. So we could have an instance where the actual center, the centroid of our beam, which may be in the middle here, is sort of offset from the center line of where your beam actually is. So the overall height of our beam will be 200 mils, which means that and we'll have the centroid be coincident with the center line of our beam. So we just make this 0.1. The beam will be 8 centimeters, so that's 80 mils in width, and it'll be that at both the top and bottom. It'll be symmetrical, and then the thickness will be 10 centimeters. It's 10 millimeters, so 10 millimeters there and 10 millimeters there. So that's the size of our beam. So we just make sure that we put all those in. And you can define these however you want. Now, one thing to note as well, we have two directions. We have this direction 1 here and this direction 2, and they'll come up of importance in just 1 minute. So we have the direction 1, which is the sort of the direction away from our beam, and we have direction 2, which is the y-axis of our beam. Alright, so we have that set up. Now we can go and we need to create our sections. So we want to create our beam section. We obviously want it to be a beam, not a truss. It'll be made out of material 1 using the I-beam profile. So the material 1 is our steel. So we can set that to hit OK, and then we can apply that to our structure. So then we go to section assignments. And we apply it to all of our beam members. So these are all our beam members. And then we just want to apply that section there. And now that's done. Now we can have a look at that simply by going to View and going Part Display Options. And we want to tick on Render Beam Profiles. Right. But we can see that hasn't been done yet because we haven't set up the when we clicked tick on that, it hasn't shown up because we haven't set the orientation. So the last thing we need to do is set the orientations. So this is where we're setting up those 1 and 2 directions. So what we'll do for the moment is we'll just select all our beam lines, right? And then it's basically asking us to give an approximate direction of the N1 vector. So remember the N1 vector was that one vector which we saw in the diagram of the I-beam before. Right. Now, if at the moment it's just heading in the global Z direction. So if I rotate around, you can see the Z direction is out this way, and here it's 0, 0, 1 or -1. So the vector of our 1 is actually heading in the negative Z direction. So if I hit that, you can see here now my 1 direction is heading in the negative Z direction. And when I hit OK, you can see the beam profiles get shown as that. So you can see those are heading off in the different directions. Now, for us, that's okay because we're going to be putting a vertical load on the end of this, so down in the negative Y direction. So the beams orientated in this direction will give us the maximum bending stiffness because that'll give us the maximum I value in that direction. However, if we wanted to rotate that beam, we can simply go back into the sine beam direction. So if I wanted to rotate these two beams, I could go in here, and rather than having them point in the negative Z direction, I might want to point them in. I might want to point the one direction in the Y direction. So I want to rotate it by 90 degrees. You can see now that the one direction is pointing in the positive Y direction, and then that will rotate the beam. Right. Now, obviously, for our scenario where we're putting a vertical load on it, that will actually be a lower stiffness. So I'm just going to rotate that back again, just by selecting my two beams and rotating it back so my one direction is in the same direction as my positive Z. Now, what I will show you is that if I try and set this up with my one direction going in the X direction, so the X direction is actually collinear with my beam's center line. So if I set this up to be 1, 0, 0, that means I'm trying to put my one direction in the same direction as my beam's center line, which is sort of physically meaningless. It doesn't actually mean it. It's a non-physical description of the system. When I go and do that, Abacus will tell me that we can't do that because the n direction is parallel to my tangent vector, which is the same thing as your beam center line. So we can't run with that, so we're going to put it instead, obviously, in the negative. We're going to put our one direction in the negative Z, which is what we see here. So if you ever get that error, that's what that's being caused due to. Okay, so we have our two beams set up. The next thing we want to set up is our truss. So for a truss, we don't have to go set up a profile because we don't need to calculate the second moment of area. All we need to do is put in the actual area. So if we just go to sections and hit create, we're going to create our truss, and it's going to be a truss type element. and the cross-sectional area on this one, we'll just make it 0.003 meters squared, which is a relatively significant amount of material. And again, it will be made out of steel. Right, and then we want to apply that to our truss element. So we're going to apply the truss section to our truss geometry here, and we put that in and it renders there. So again, like we said before, because we don't really care about the second moment of area of a truss, it always just renders it as a solid circular section. Alright, so a couple more things to do here is we need to now mesh our part. So if you open up our crane part, we can go down to mesh and switch context. So two things here. With the truss element, as we did with the previous tutorials, with truss elements we only ever want one truss element per bit of geometry. So here we only want one element for our truss, but for our beam element we can have multiple elements. We can have quite a number of elements if we please. So what we're going to do is we're going to set our global seed. So this global seed will set a global size of 0.25 meters per element, and that will apply to the whole system. Alright, so if I hit apply, and I'm actually just going to, for the moment, hide my profiles, my element profiles. So when I hit, when you can see the size that's been applied there, the 0.25 meter global element size, and you can see that at the moment that's also being applied to our truss member. But we can override that by using a local seed. So if you go up here to the left, you can see it says seed edges. This is where we can apply local seeds, and a local seed will always override or take precedence over a global seed. So you can set up a global seed for your system, but when you're going to go and apply a local mesh seed, that will override it. So I want to apply a local seed to this geometry, and I want to have one element on that bit of geometry. So you can see now here it's put up a seed where I don't have any internal nodes inside of that element. Alright, so that's all good. Next thing we want to do is set up our element types. So we want to go assign element types. So here I want to apply all my beam element types. So we're going to use just linear beam elements. So go down to my beam element family and just choose linear elements and hit OK. But for my truss element, I want to, obviously we don't want to use a beam element, we want to use a truss element, and again we'll just use linear, a linear truss element. And now we're done with that. So that sets up that analysis all nicely. Last thing to do with that is just to mesh the part, and we mesh it, and you can see down the bottom here we have 34 elements. Now we can have a bit of a better look at that by just going by tools and going to query, and we can go down to the element part, and we can see here that we have one element here, and then we can see all our other elements along our beam. So this is exactly what we wanted, and it shows down here what type of element you have as well. So we can see here this truss element is a three-dimensional truss element. It has two and it's just a linear element, so that's the T3D2 element. We can see here that B31 is a beam element acting in 3 dimensions, but it's only linear. So that's what we have out of that. So yeah, alright, cool. Now next few things to do is just set up our boundary conditions, and we can go and do our first solve with this. So the first boundary condition we're going to set up is we're going to go, actually we need to set up our assembly. Forgot to do that. So if we go back to our assembly, and go into instances, we can just import our crane, and the actual next thing we need to do is set up our loading step, as we always do. Alright, so now we can go ahead and apply our loads. So the first thing we're going to do is put a force here of 200 kilograms, so about 2,000 newtons. So I'm going to put in a vertical load here. It's going to be a concentrated force because it's just going to act on a single node. So we're going to apply it to this node here, and it's going to be in the negative y direction, so it's negative 2,000 newtons, and again we're working in SI units. Okay, so that's acting on that, and the other thing we're going to set up is a boundary condition. So we're going to create a fixed boundary condition, fixed to ground, and we're going to use a displacement rotation, and we're going to apply it to it, not just to that bottom node. Now, remember here we have a three-dimensional system, and so for this to be in static equilibrium, we need at least 6 degrees of constraint. So we need to constrain this thing in the U1, U2, U3, as well as the rotational degrees of freedom as well. So that point won't be able to move translationally or rotate. Okay, so we have our system set up, and now we can just do a simple analysis on this. So we can go to our jobs manager. We're going to create our crane job, and we can just submit that and look at our results quickly. Okay, so that looks like it's run correctly, so now we can just go to the results. And if we look at our model here, so we can look at the stress in our system. We know we have the von Mises stress, but we can also look at, we'll just look at the, well actually, yeah, we'll look at the S11 stress, so that's the, just your stress in the local X direction. So you can see here that this is all, well, we can see in the beam, sorry, in the truss element, we can see we have just a normal consistent stress, which is what we expect. But remembering that with the beam element, the stress, the normal axial stress that we find in our element is dependent on the distance from the centroid, is dependent on the Y value. So what we have here is we have the stress in the axial stress, so that's the S11, but it's on the lower flange, which is basically, if we bring up our section again, so if we go to the beam section, sorry, not beam section, but the beam profile, so we can have a look at that. So we're looking at the stress on the lower flange, so that's the stress down the bottom edge here, right? So at the furthest distance away away from the centroid in the one direction, in the two direction, so that's along this bottom edge here. So if we go back to our results, oops. So we can see that we're getting compressive stresses on that flange here. Now, obviously, for a beam like this, you'd have the exact same forces, but reversed on the other side. So you can see here that we're getting reasonably high stresses. So we're getting stresses at about sort of 10 megapascals at the top here. All right, so that's a very basic beam analysis. What we're going to show you now is how to do a couple of little more extra things as well. So if we go back to our model, one thing we note is that with this load, we've created a concentrated load. Now, in general, in a physical world, you never really have concentrated loads. No, loads are never applied at a single point in space. It's pretty much physically impossible to do that. Typically, loads will be applied over a distance. So while we have a system here, we're applying the load over that distance. We know that it's definitely not the most accurate way, physically accurate way of doing it. It'd be better to apply the load over a distance. Now, in our system, in our jib crane analysis, in reality, if we go back to our part, we know that we could imagine that the actual load being applied here would be applied over a distance, and that distance might be around 200 millimeters. So remembering that the distance from here to here is 2.2 meters long, so we can measure that. So if we go to query, we can go to distance, and we can measure the distance from here to here, and we see that that is 2.2 units, and here we're using SI units, so that's meters. So it's 2.2 meters. So we actually want to apply that load, that 2,000 newtons, over a 200 millimeter distance. Now we can't do that at the moment because we haven't, we have no edge there. The only edge we can select is that full 2.2 meters. So what we need to do is break that edge up a little bit. So there's two ways we could go about doing that. So the first thing is, if we go into our feature, we could go back into our sketch and actually edit it, edit our sketch and put in another point in there. That's one way we could do it, right? Simply by just breaking up the length of that line and going forwards from there. Another way we could do it was we could just add in another feature. So to do that, what we're going to do is, if we go to our crane, and if we go to our frequently used tools over to the right here, we can go down to this one here. So this position here, if you just click and hold on it, we want to go to this partition edge system here. So we have two options to partition edge. We have it just the normal one here, which goes halfway between it, or we have the partition edge, where we actually specify what percentage along our along our edge do we want to split it up, and that's what we want to do here. So I'm just going to go to this one. So I'm going to select the edges you want to be partitioned, which is just this edge. It's going to tell me that if I do this, I'm going to delete the mesh. I need to delete the mesh to do it, so we just need to remember to reinstate the mesh when we fix the system up. And then it asks us how far we want to go along. Right, so we can see here that this is this value is allowed to vary from 0 to 1, where 0 is going to be, we can see here the arrow points to the right. So if I set that as 0, well, I'll set it to a low value, sort of to a value of 0.1, you can see the edge is partitioned to the left hand side, and if I set it to be 0.9, the edge gets partitioned to the right hand side, which is more what we want. So we want it to be 200 mils to the right hand side. So you can actually enter in basic mathematics into these text fields. So I want it to the left hand side, so I want 200 mils to the left hand side. I don't know what proportion that is. I can't be bothered whipping out my calculator and calculating it. So I know that's 200 millimeters to the left hand side, and that's over 2.2 meters. Now if I hit enter, that's actually going to end up on the left hand side, but I want it to the right hand side. So to get that to the right hand side, I just need to do 1 minus, and it puts that to the right hand side, and I can just hit create a partition from that. Now if I want to make sure that that is 200 millimeters, I can again just go to my distance tool and just measure the distance of that element. Oh, whoops, sorry. Let's measure the distance from that node to that node, and the distance there is 200 millimeters. Oops. So the distance there is 200 millimeters, so that's set that up fine. So it's much easier to do math inside of those text fields rather than doing the math in a calculator or writing it down by hand and then putting it in. Okay, so we set that up, and now we can go down to our loads, and now we have our vertical load. Now we're not going to delete, we could either delete this load out, or alternatively we could just suppress it for the moment. So when we go to our loads and hit suppress, it just means that currently that load's not going to be applied, but we can still keep all the detail of the load there if we want to use it later on, which can be useful. So we're going to create another load, and we're going to have this as a distributed load, right? And the way we do that is we're going to use a line load. So a line load is effectively a distributed load. So here we're going to apply it to that edge, right, that 200 millimeter edge. We're going to select that one and hit done. And then we need to put the value in here. So just remember that when we put the value in here, if I put this as, like we had before, 2000, I think we had 2000 is what we had before. If I put that in, that would be 2000 units of force per distance, so that would be 2000 newtons per meter. Now we don't have that. We have 2000 newtons overall over a distance of 0.2 meters. So again, I can just use math inside of this context. So I know it's 2000 newtons over 0.2 meters. and again it's negative because it's going downwards. Alright, and we see that there. Alright, so we have that all set up, and now we can just go in and solve this again. So if I go back to my jobs manager, I can hit submit. Oh, we didn't set up the mesh, of course we didn't. So we need to go back up and set up the mesh again. So if I go back to my mesh, we're just going to apply the global seed again to my system. I'll just, and then we also need to reapply what type of elements we want to these two parts. So we need to do it to both sections because both of those meshes got deleted. And we're going to apply a linear beam element to those two. And hit done, and then we can remesh our system, and we still have 34 elements because it's the same basically geometry, it's split up slightly different. And now again we should be able to go back and run our job. Alright, so that job's run fine, and now we can go look at the results for that. They should be very similar. Alright, the only thing we've done is essentially I think, as long as our loads are correct, I might just unsuppress this quickly. Sorry, resume it. Yep, yeah, that should be all fine. So just resuppress that, go back to my results. So we have a relatively similar result. What we might want to check in this instance is that the overall reaction force is the same. So we can go back down to, if we change the thing we're looking at from stress down to RF, which is the reaction forces, it'll show you that down the bottom here, where it's red, so that's our maximum, we have a reaction force of 2,000 newtons, which is what we want. We're applying 2,000 newtons here, and we're getting a reaction force of 2,000 newtons. We can also see what reaction moment is being generated there. We can go down to RM, and we can see that we have a reaction moment here of 7,200 newton meters down the bottom there. Okay, and the last thing we'll show you how to do is how to add in another member. So if we looked at this analysis, if we looked at this system, and if we looked at the stress, for example, and we were not satisfied that this stress, we thought that this stress was too high, we could go in and put in another element. So let's do that. So if we go back to our part, again we could go in and modify the original sketch that we drew, or we can just go in and put in a new element. So I want an element to go from the end of where we're applying a load back down here. I think that that's a good idea. So to do that, I can go to my frequently used buttons here, and you might have a system which looks like this. So you just want to press and hold on this button here and go to the create wires tool, and we want to add in a new wire, and we want it to go from this point here to wherever that point is there. Right. So we want to put in a new truss member in between those 2 points. And we are done. Just make sure you only have one wire in there, and we're good to go. Now obviously we need to assign a section to that new truss member. So we go to the section assign tool, and we select that member, and we're just going to select the truss. And we will also need to mesh that system. So again, we'll apply we don't want to use the global seed for this, we want to apply a local seed, and we only want to use one element. And then we can go and we want to choose what type of element, what types of element we want to apply to that truss, which is obviously going to be a linear truss element. And we want to mesh the whole part again. And remember, we've gone from 34 elements to 35, which makes sense because we only wanted to add in one element in there. Alright, now everything else should be good to go, and we can go ahead and go back to our jobs manager, submit this job, and we should just be able to quickly review the system. And we should see that if you go look at the results, we should be able to have a look and see that that has now taken effect. Right. So we've only slightly reduced the stress, because obviously what we should do is bring that trust member down here and put it some way down here. So what I might leave you guys to do is basically redesign this trust system and try and get the stress down below 25 megapascals by just adding in different truss members. So you may want to move this truss member from, rather than pinning to here, that it pins down further down here. So adding in a secondary brace. Alright, thanks guys. Bye.